This video looks at when the real axis is part of a root loci. So a reminder of the overview. We've already looked at what are root loci and why they're important. And here we're focusing on how do I compute root loci and produce some sketches. This particular video is looking at identifying when the real axis is part of a root loci. So a background, you'll remember we're looking at simple feedback loops of this form with a compensator M and a system G. We're going to simplify Gm by writing it like this, Kn over D, so we've extracted K as a scalar gain, and then we're saying that you can calculate the closed loop poles in a number of different ways. You can solve Kn over D equals -1, or Kn plus D equals 0, and you can also observe that at a closed loop pole the argument of n minus the argument of d is 180 plus or minus n times 360. So what are we going to do here? We're going to expand n of s and d of s in terms of open loop poles and zeros, and we're going to ask ourselves when is some value s equals hi on the real axis and also a closed loop pole. So you'll notice we've said here, let zi be the zeros, pi be the poles. Then I can write my numerator polynomial as hi minus z1. Remember, hi is in place of s here, times hi minus z2 and so on, to hi minus zm. And I can do a similar trick with the denominator. Now what I want to do next is compute the phase of each of this n and d. So this is what we get. If hi is greater than z, then the argument of hi minus z must be 0. Now remember, here we're assuming that z is a real number and that h is a real number. So if h is bigger than z, you've got the argument of a positive number, which is 0. Conversely, if h is smaller than z, you've got the argument of a negative number, so you get 180 degrees. So what's the summary? If z is to the left, and we mean to the left of this particular point we've chosen, then the phase is 0. If z is to the right, then the phase is 180 degrees. Now, you'll have noticed that we didn't talk about complex roots, and the reason is that if you have complex roots, they always appear in complex conjugate pairs, and in that case you'll find that the argument of the quadratic factor will always be 0 or 360 when s is a point on the real axis, and therefore those complex roots will not affect the arguments we make in this video. So here's an illustration. You'll see I've put a point on the real axis. There it is. That's essentially doubling as the point s, but here I've called it h, and we want to work out what's the argument of h minus z2. And clearly here it's going to be 0, because you'll see it's a positive number. What if we were to put z over here? Well, if we were to do that, then h minus z is now this way, and so the argument of h minus z1 is clearly 180 degrees. Now why is this important? In this particular case, this z is to the right and this z is to the left. So what does that tell you? If the 0 is to the left, you get 0 degrees. If the 0 is to the right, you get 180 degrees. Here's a different illustration. Now what I'm going to ask you to do here is to calculate the argument of this n of s up here, where I've substituted s equals hi, and you'll see I'm going to put different values of h, and you'll notice I've marked for you the points z3, z1, z2. So let's start with this h1. h1 minus z1 is this. z3. h1 minus z1 is this, and h1 minus z2 is this. So you'll see that you get the argument of h minus z1 plus the argument of h1 minus z2 plus the argument of h1 minus z3, and in all these cases you'll see you get 0 plus 0 plus 0, which equals 0, and the key thing is that all zi are to the left. You can see that they're all to the left, and they all give you a 0. Now let's consider a different point. See this H2, and I'll use red here, that's marked here. And now we want to do a similar calculation, except we're going to do the argument of H2 minus Z1 plus the argument of H2 minus Z2 plus the argument of H2 minus Z3. Now in this particular case, you'll see this one is negative, but these two are positive. So H2 minus Z1, the argument 0, H2 minus Z2, the argument 0, but H2 minus Z3, you get 180 degrees. And you notice here, Z3 is to the right. And because it's to the right, you get 180 degrees. And now final example. Let's look at H3. And I'll use black for this one. It's getting to be a bit messy now, so there's H3. So in this particular case, we're going to do the argument of H3 minus Z1 plus the argument of H3 minus Z2 plus the argument of H3 minus Z3. And your H3 minus Z1 is going to give you 180. H3 minus Z2 is going to give you 0. And H3 minus Z3 is going to give you 180. And so what you notice in this case, Z1 and Z3 are to the right. And so you get 180 degrees for each of those. So what have we got? If we put the summary, if something is to the left, the phase is 0. If something is to the right, the phase is 180 degrees. So the overall argument for n of s is going to be 180 times the number of zeros to the right. The overall argument of d is going to be 180 times the number of poles to the right. That reminds you what n and d are given us. So in summary, for a given value of hi on the real axis, the argument of n minus the argument of d will be equal to minus 180 plus n times 360 if the number of zeros plus, that's key, you've got to add them there, the number of poles to the right is an odd number, because you get 180 degrees for every zero and every pole which is to the right. And you'll notice this 180 times n360 gives you an odd multiple of 180. So what have we got? The loci is on the real axis if there is an odd number of open loop poles and zeros to the right. And this observation has simply come from matching the phase of kn over d to 180 plus or minus n times 360. So, if S is a closed loop pole for some k, then you can solve this expression. And what we've just shown is that the real axis can satisfy this particular expression. So the real axis satisfies this expression if you have an odd number of open loop poles and zeros to the right, and as long as you can satisfy the phase criteria, so if I write that here, this is a phase criteria. Once you've satisfied that, you can always find a suitable value of k to satisfy the gain criteria. So some examples. Where are the loci, the root loci for this system on the real axis? And you notice we've given you a start point by telling you where are the poles and where are the zeros. So let's mark this using a figure. So you'll see we've got a pole here, a pole here, and a pole here at 0, minus 1, and minus 2. And what we need to be doing is counting odd. So if I'm in this region here, you've got 0 to the right. You'll see if I do myself a little eye and I look that way, you'll see there's none. If I'm in this region here, I've got 1 to the right, and you can see which one that is. It's the pole at 0. If I'm in this region here, I've got 2 to the right. And if I'm in this region here, I've got 3 to the right. Now the next question is, we said you're on the loci if and only if the number to the right was odd. So that means I've got to have 1 to the right, but not 2, or I could have 3 to the right. So that hashing marks the parts of the real loci, or the parts of the real axis which are on the loci. Here's another example then. So I'll do a sketch so we can see where all the poles and zeros are, and from that you'll notice this rule is very easy to do. So first of all, I've got a 0 at 1, I've got a pole at the origin, I've got a pole at -1, a pole at -2, a pole at -3, and a 0 at a half. And you remember, I've got to count whether I've got an odd number to the right. So here, see this bit I've hashed, and I put the number there, I've got 1 to the right. Next, in this region here, I've got 2 to the right, so I'm not going to hash that. Next, in this region here, I've got 3 to the right, so that is on the loci. Next, in this region here, I've got 4 to the right, that's an even number, it's not on the loci. And finally, in this region here, I've got 5 to the right, so it is on the loci. So conclusions. We've introduced the rules for when the real axis is on the root loci. In essence, you count the total number of poles and zeros to the right, you ignore complex roots because those are always in pairs, and if this number is odd, then that part of the axis is on the loci. Now the next video is going to look at all the 5 rules we've given and go through a number of worked examples to produce whole sketches.